Welcome back to the Advanced Software Architecture course. My name is Michel Chaudron and this is the lecture Quantitative Analysis of Software Architectures Part 5 on Reliability Block Diagrams. Reliability Block Diagrams. A reliability block diagram, abbreviated RBD, is a graphical depiction of the system's components and connectors, and it can be used to determine the overall system's reliability given the reliability of the components. An RBD can have one or more paths through it, which represent successful operation. Blocks represent system components. The diagram shows which paths through the blocks are essential to success. If any path from left to right is executed successfully, then the overall system is said to succeed. Otherwise, if all paths fail, then the system fails. There are several important assumptions that accompany reliability block diagrams. First of all, the reliability of each individual block is known or estimated. The lines have a reliability of 1, and all lines share the same semantics. The failures of blocks are statistically independent. Blocks are bimodal, they either operate or they fail completely. So a degradation of service or introduction of noise is not allowed. Moreover, all successful paths are shown in the diagram. Given these assumptions, it's possible to calculate the reliability of a system expressed in terms of a reliability block diagram. The reliability of each component in a reliability block diagram can be given in a variety of ways, either as mean time to failure, as reliability percentage over a period of time, or as a failure rate. We will often use failure rates in this lecture. From a component's failure rate lambda, we can derive the reliability of that component over a period of time t using the equation on this slide. For example, if a component is estimated to have a failure rate of 10 failures per 1000 hours, then its reliability over a 24-hour period is calculated to be approximately 79%. Try if you can repeat this calculation for yourself. Next, we look at some common patterns in reliability block diagrams. The first pattern we look at is that of a chain of components. It is composed out of blocks that are put in sequence. It means that a computation must pass through all the blocks. The overall reliability of such a pipeline or chain can be calculated as the probability of all components executing successfully, hence the product of the individual reliabilities. You can look at the example. Here's the other common pattern in reliability block diagrams. This denotes alternative or parallel components. In this case, the overall reliability of a system is 1 minus the probability of all components failing. Essentially, it indicates alternatives. At least one of the components must offer a service for a computation to pass through the system. Here's an example. Please look at the calculation carefully. When you do the calculation yourself, please take into account the accuracy or precision of the numbers that you calculate with. Here's an example of reliability based on a structural view. In a software architecture description, we use component diagrams or class diagrams for representing the structure of the system. These diagrams show dependencies or usage relations between components. If you look at the structure of this diagram, it is not automatically, not in general, the same as that of the corresponding reliability block diagram. Often, some transformation is needed. The following example illustrates the reliability analysis of a simple system. Consider a system of 5 components, C, S, K, L, and M, arranged as shown on the slide. C and S suggest to be clients and servers, and K, L, and M are services to S. Now, in addition to the structure of the system, we actually need information about the behavior of the system in order to know if components are mandatory steps in a flow or alternative steps. For this, we would need to know the control flow. The control flow tells us which paths are taken through the system. In this slide, we suppose that all of K, L, and M are mandatory. A service needs to be processed by all of them. Therefore, the corresponding reliability block diagram consists of all these components in sequence. Here is another example for reliability based on the structural view. We consider again a system composed out of 5 components, arranged as on the slide. However, in this example, we suppose that K1, K2, and K3 are alternatives to each other. But also, the flow we consider must pass through components C and S, as illustrated through the red dotted line as a control flow through the system. Therefore, the corresponding RBD consists of all components C and S in sequence, followed by the parallel or alternative composition of K1, K2, and K3. A reliability block diagram is not correct unless there is a complete flow from start on the left typically to the output on the right. So the diagram must show how the outputs of K1, K2, and K3 are combined. In this example, we illustrate how to handle the time sharing of computational resources. Here, software components K, L, and M, as well as S, are all deployed on one hardware processor, and component C is deployed by itself on a separate hardware node. When we assume that K, L, M, and S each get an equal share of the time of processor X, then their failure rate gets divided by 4, because they get scaled down to 1/4 of their original time. Here are some heuristics for applying reliability block diagrams. Formally, not all systems can be reduced to series parallel graphs that we have shown are the key patterns in reliability block diagrams. So sometimes you may need to simplify the design. In this case, you can look, for instance, at the critical paths through the system, because the paths typically are series parallel graphs. Moreover, you can consider how much time is actually spent per component and use that to refine your calculation. And the good news is that there's actually tools around, you can probably find them on the internet, that help you compute the reliability of block diagrams. Here's a summary of today's lecture. We showed a simple method for analyzing the reliability of systems at an architectural level. In previous slides, we also showed that simple analysis methods exist for analyzing performance and timeliness. I hope that our lectures have convinced you that doing such type of analysis require little effort, but provide lots of value to the project. They provide value through increased understanding of whether a system meets the non-functional requirements. Moreover, performing such analysis reduces the risks in the project. In summary, a best practice for the architect is, if you haven't analyzed it, don't build it. Do we have text here?
No, we don't have text. Maybe, okay, just do exercise.
For those of you that want a more in-depth understanding of reliability and reliability block diagrams, we recommend to start by looking into the papers mentioned on this slide. The lecture Quantitative Analysis of Software Architecture Part 5 is finished. Thanks for listening.